All right, so in this video, we're going to be looking at finding the inverses of one-to-one functions. Now, sometimes this is completely straightforward. The algebra is not difficult, and the inverse is very easy to find. So, for example, if you have a linear equation, you would simply write your function notation, remove it, switch your x and the y values. So x is equal to 3y minus 2, and then just do the algebra that you need to do to get y by itself. So in this case, I would add 2 to both sides, and then I would divide by 3, and that's going to give me y is equal to 1/3 x plus 2/3. And if we want, we can double check that this is in fact the inverse. By composing f with the inverse. So I take my original function, I stick in my inverse, and when I distribute the 3's, I get x plus 2 minus 2, which is give me x. If everything cancels out and you get to x, then this is in fact the inverse. Another easy example would be something like a cubic function. As long as it doesn't have a bunch of extra x and x squared terms, then you can do this also very easily. Find the inverse. We would switch our x and y, solve for y, so I put the 2 over to the other side, take the cube root, cube root, not the square root. And so my inverse is the cube root of x plus 2. And then, again, you can check it with the composition. The cube and the cube root will cancel, and then the constants will cancel out, and you'll end up back with x. As long as everything cancels to x, you're good. And you can do it in the substitution in either order, because both have to give you the same simplification. The original function is the inverse of your inverse function. So now, when things get a little bit more complicated is when you have a rational function. So let's look at an example like this. Now, this function, it does turn out is 1-to-1. It has a horizontal asymptote at 1/3, and it has a vertical asymptote also at 1/3. And so this is something that it is in fact 1-to-1. It's not one of those other types of rational functions where there are multiple asymptotes and you get, weird behavior going on in the middle. So we can find the inverse of this, and the procedure mostly begins the same way. The issue, though, is going to be that the algebra is a little harder. So x is equal to y plus 2 divided by 3y minus 1. Again, the algebra is not hard. There's just a little bit of a trick that you have to remember to do. So I'm going to multiply both sides by the denominator. So x times 3y minus 1 is equal to y plus 2. I'm going to distribute 3xy minus x is equal to y plus 2. Now at this stage, what I need to do is I need to collect my y's on one side of the equation and everything that is not y on the other. So 3xy, move the y over by minusing it, and then add x to the other side. Now we factor out the y on the left side. And then we divide out our coefficient and get it back to the other side. Now, the interesting part about this particular function is that it turns out it is its own inverse. Most rational functions are not going to do that. You're going to have the constants moved around and different things in different places. But it turns out that in this particular case, the horizontal and vertical asymptotes are identical. And in fact, you do end up with the function turning out to be its own inverse. Now, one of the things that will happen when you have inverses of functions, inverses have symmetry, but they have symmetry with the line y equals x, because that's the y equals x is the swap that we've done in order to find these functions. So one thing you can do to check your answers is to go to a graph and plot the graph. And so let's do that for each one of our examples. So we'll go back up to this one. Let's plot this equation versus our original equation and see what it looks like. Now, if we look at our graph, and I'm going to insert it here, you can see that the original equation is your 3x minus 2. Your inverse is the 1/3 x plus 2/3. That's the blue line here. And then I've also drawn on the line y equals x because that's the line of symmetry. And you can see that as these two lines separate from each other, they are separating at a constant rate relative to each other. The point of intersection is directly on the line y equals x because that is a point on both graphs. And this is the kind of thing that you would expect when you're finding axes of symmetry. Again, if you imagine folding your graph across that green line, the two sides of the graph should line up. Now let's try the same thing with our inverse for our cube function. And if we just insert the function graph here, again, we see the same kind of thing. We have our line y equals x, and across that we see this symmetry from our two graphs. Now finally, let's do the third graph, and we can see why the original graph is its own inverse. Now, in this case, I've only plotted the one function because the function and its inverse are the same. And you can see that across this line, y equals x, it does have symmetry with itself, which is why the graph is its own inverse.